String theory proposes the wrong number of dimensions of space. For instance, it proposes the wrong sign for the cosmological constant. For instance, the Big Bang theory proposes that the universe originated from nothingness, marking its beginning. Before this event, there was no time or space. However, what if I told you that time doesn't actually exist and the Big Bang theory could be incorrect? That's the view held by renowned scientist and Nobel laureate Sir Roger Penrose. Penrose is among those who argue against the idea that the universe emerged from nothing. He suggests that there was neither a beginning of time nor of the universe itself. What's particularly intriguing is his belief that dark matter, often theorized to exist based on astronomical observations, is not actually present in the universe. Now you may wonder how the recent data supports the concept of time having no beginning and why Roger Penrose disputes the existence of dark matter in the universe. There is this dark matter which seems to be out there and dominates the material of the universe. It's by far the majority of the material substance in the universe, and it's called dark matter, but nobody really knows what it is. It seems to be the major part of the mass of a galaxy and was first observed because of the stars going around too fast in order to compensate for the extra attraction of this dark matter. All sorts of cosmological observations tell us it's there. Now, if it's there, and if it's really gravity because it's picked up on the gravitational degrees of freedom, there's nothing else in physics going on with regard to it. It tells us something about what it ought to be. One thing it ought to be, and I think I've listed these things here if you can read them, is its mass. Well, the only thing it can be, if we've just got gravity, roughly speaking, is something called the Planck mass. It might be 8 pi times it or something like that, but it's of the order of a Planck mass. How big is the Planck mass? It's about 10 to the power of -5 g. That's about the mass of the eye of a flea. I believe I got that from Google or something. Now that is huge if you're talking about particle physics. In 1981, many of the world's leading cosmologists gathered at the Pontifical Academy of Sciences, located in Villa within the Vatican Gardens. In this setting, Stephen Hawking chose August to present what he later considered his most important idea, a proposal on how the universe could emerge from nothing. Before Hawking's presentation, both scientific and theological explanations of the universe's origins faced the same question: what happened before that? For example, the Big Bang theory, introduced by Belgian physicist and Catholic priest Georges Lemaitre, traced the universe's expansion back to a hot, dense bundle of energy. Yet the question remains, where did this initial energy come from? The Big Bang theory also faces other challenges. Physicists know that an expanding ball of energy would likely become a chaotic mess rather than the smooth, vast universe observed by modern astronomers. Stephen Hawking, renowned for his intelligence, offered a unique solution to the quest to look back in time. He suggested that there's no beginning or end at all. During a Vatican conference, a 39-year-old physicist from Cambridge University, still able to speak, addressed the audience. He proposed that the universe's boundary conditions must be truly unique, suggesting that the most unique condition could be that there is no boundary. This no-boundary proposal, fully detailed in a 1983 paper by Stephen Hawking and his collaborator James Hartle, envisions the universe as a sphere. This sphere starts with a diameter of 0 at its bottom point and gradually expands. According to this proposal, the universe smoothly expands from a point of 0 size. Hartle and Hawking formulated an equation describing the entire sphere, the wave function of the universe, encompassing the entire past, present, and future simultaneously. This prompts contemplation on the seat of creation, the creative force, or any transitions from a time before. In a 2016 lecture at the Pontifical Academy, Stephen Hawking stated that asking what existed before the Big Bang is meaningless. According to the no-boundary proposal, time as we understand it does not exist. Hawking likened this to asking what lies south of the South Pole. Both questions don't make sense. The Hartle-Hawking proposal fundamentally redefines time, suggesting that each moment in the universe is like a cross-section of a sphere. While we see the universe expanding and evolving, real time involves the relationships between the universe's size in each cross-section and other properties, especially entropy or disorder. Entropy increases from the bottleneck to the feather, indicating an emerging arrow of time. However, near the bottom of the sphere, these correlations become unreliable. Time ceases to exist and is replaced by pure space. As Hartle, a professor at the University of California, Santa Barbara, explained, "We don't have time in the early universe, but we have it later." Thus, time doesn't have a starting point in this no-boundary condition version of spacetime. Hawking proposed a version of the universe without a beginning or end. As you approach this initial stage, it transitions into what's called imaginary time. In theoretical physics, the Hartle-Hawking state, named after James Hartle and Stephen Hawking, describes the universe before the Planck era. Hartle and Hawking suggested that if we go back in time to the universe's origin, we would find that time transforms into space as we get closer to the beginning. This means the very start was only space with no concept of time, making the idea of a beginning irrelevant. According to the Hartle-Hawking proposal, the universe doesn't have a traditional origin, it's a singular point in both space and time. Before the Big Bang, therefore, the Hartle-Hawking state universe doesn't have a distinct starting point, differing from the whole steady-state universe concept. Instead, it lacks an initial boundary in both time and space. The Hartle-Hawking state represents the universe's wave function, a theoretical framework to explore its origins, calculated using the Feynman path integral. Specifically, it's a hypothetical vector within the Hilbert space of quantum gravity theory that defines this wave function. This function depends on the metric tensor defined across the compact d-dimensional surface of the universe, where d represents the spacetime dimensions. The precise form of the Hartle-Hawking state involves integrating over all possible d-dimensional geometries that satisfy the necessary boundary conditions. According to this theory, time becomes distinct from the three spatial dimensions as we currently understand them. Once the universe reaches the Planck age, a wave function like this can satisfy the Wheeler equation. Imaginary time serves as a mathematical concept in certain approaches to special relativity and quantum mechanics. It plays a crucial role in connecting quantum mechanics with statistical mechanics and is utilized in various cosmological theories. Mathematically, imaginary time represents real time transformed through a Wick rotation, where its coordinate is multiplied by the imaginary unit I. Now, contrary to its name, imaginary time isn't unreal or fictitious in the sense of challenging rationality, akin to irrational numbers. Instead, it's a concept expressed through imaginary numbers in mathematics. Some may see imaginary numbers as merely a mathematical concept divorced from reality. However, from an empirical philosophical standpoint, defining what is real is not straightforward. Our task is to develop mathematical models that accurately describe the universe we live in. Interestingly, a mathematical framework that includes imaginary time not only explains observed phenomena but also predicts others that we have yet to measure, based on compelling reasons. So, what defines reality versus imagination? Could the distinction be purely subjective? In the theory of relativity, time is multiplied by the imaginary unit I. This can be interpreted as a reflection of the intricate relationship between space and time, or it can redefine time itself as imaginary time, adjusting the equations accordingly. In cosmological physics, imaginary time plays a role in various models of the universe. By integrating imaginary time into the equations from general relativity, scientists can address singularities where the known laws of physics cease to apply. For instance, the Big Bang appears as a singularity in normal time. However, in models using imaginary time, this singularity can be resolved, allowing the Big Bang to function like any other point in four-dimensional spacetime. Before the Big Bang, there existed nothing but a vast expanse of energy and time. The ongoing scientific debate about imaginary time inevitably leads back to questioning the validity of the Big Bang theory. Since the launch of the James Webb Space Telescope in 2021, increasing scrutiny has highlighted uncertainties and gaps in this theory, which has been central to cosmology for over a century. A major point of contention revolves around the formation of light elements, such as lithium and helium. According to the Big Bang theory, these elements, including deuterium, were supposed to have been produced during the explosive birth of the universe. For instance, the theory predicts the creation of approximately 400 lithium atoms for every billion hydrogen atoms. However, astronomers studying ancient stars within our galaxy have discovered inconsistencies with these predictions. They've observed that the amount of lithium present in these earlier-form stars does not match with what the Big Bang theory anticipates. These stars, which originated very early in our galaxy's history, contain minimal quantities of heavier elements like iron, which are generated by earlier generations of stars. This disparity challenges some of the core assumptions of the Big Bang theory, prompting ongoing reassessment and debate among scientists. In many of these stars, the lithium abundance is only about 160 lithium atoms per billion atoms of hydrogen, which is significantly lower than what the Big Bang theory predicts. Furthermore, recent data collected over the past few years shows that older stars actually tend to have even less lithium. A study presented by Lana at the January 2020 meeting of the American Astronomical Society highlighted that observations of lithium and helium abundances in these aging stars deviate markedly from predictions, surpassing what could be attributed to chance or statistical error. This undermines the Big Bang theory's claim that these light elements formed at the moment of cosmic birth, casting further doubt on the prevailing scientific model.